Hello everyone, my name is Mahtab Sarvmaili. I'm a PhD research fellow at Dalhousie University under the supervision of Professor Stan Matwin. Today I want to present the using of deep reinforcement learning methods for autonomous vessel navigation in 2D environment. The materials I cover today are listed here. First, I will talk about the essential terms and definitions that we exploited in our paper. Then, I will explain our model and the baseline that we used to compare our algorithm. In the next part, I will talk about our test environment and some formulas that we exerted in our implementation. For the next section, I will dive deep into the details of a training and testing setup and the whole procedure that we followed. The next part will be about comparing and analyzing the results of our model with the baseline. Unmanned surface vehicles technology is an exciting topic that essentially deploys an algorithm to safely and efficiently perform a mission. With the growth of machine learning algorithms, autonomous vessel navigation has attracted a great deal of attention among scientists. Deep reinforcement learning is one of the machine learning algorithms which has been proved to be effective and efficient in training the autonomous agents in complex environments. Also, path planning methods have been traditionally exploited to generate the efficient path between an initial location and desired destination. So, in this paper, we aimed to design a new method by combining these two concepts for vessel navigation and obstacle avoidance in marine environment. Our algorithm uses deep reinforcement learning and local view strategy, which is called Vessel Navigator with Planner and Local View, VNPLV, for training the agent. In this part, I explain the main concept used to model our agent environment approach. In this work, an agent is a vessel voyaging from an origin in the environment with the objective of safely arriving at the desired destination in that environment. The environment is a bounding box area that contains a body of water that an agent can voyage through and a variety of lands which the agent cannot travel through them. Our agent can take some actions from a set of 8 directions to move from its current location to its next location. An origin point is the position of an agent at the first moment of a training or testing phases. The destination point is the final geographical position that an agent should arrive at. After taking the action in each state, there will be 5 discrete outcomes: hit an obstacle, hit land, to arrive at target, to vanish target, and normal movement. Hit an obstacle means that the agent hits one of the vessels moving in the environment. To hit the land means that the agent took a direction that moved it to a geographic area that has land. To arrive at target means that our agent successfully reached its destination point. To vanish target means that the agent is farther from the target than the distance threshold. Finally, a normal movement is an output where the agent has not finished its mission, but there is no reason to stop the voyage. As you can see in this picture, each action and its outcome for our agent in the environment is considered as one step. Therefore, each step moves our agent from a current state to a future state. On the other hand, an episode is a set of consecutive steps with a fixed origin and destination point. Another important element is the plan and its outcome. Similarly to the episode, a plan starts with an origin point and ends with a destination point, and it includes a set of episodes. If the outcome of the last episode is reaching to the destination, that plan is a successful plan. On the other hand, the outcome is anything except reaching destination. It's considered as a failed plan. One of the important contributions of our paper is limiting the knowledge of our agent about the environment so that the agent is only able to observe within the boundary around itself, which is called the local view. This approach forces the agent to learn general rules of movement without memorizing the whole environment and the best path. Each one of these local views should have its goal to guide the agent. But when an intermediate goal is outside of our agent's local view, we find its shadow on the boundary of the local view and we choose it as the goal in that specific plan. Here we present the internal structure of the baseline that we choose to compare our algorithm with. The vanilla vessel navigation is the baseline. You can see its internal structure in this picture. The origin point, destination point, and the current position of the vessels are the only inputs that this model takes from the environment. The output of this architecture determines the best action to select in that specific state. Now in this slide you can see the structure of our model, vessel, navigation plan, and local view. Our method benefits from two planning modules. First is the path planner that provides a long-term plan using the fluid algorithm without considering any dynamic obstacles on the way to arriving at the destination. This can be seen as a high-level planning without considering the details of a plan. After that, we reduce this high-level plan by removing similar intermediary goals by applying the Romer-Douglas-Pecker algorithm. In the third step, our agent decides on the details of the plan in the near future to arrive at the shadow of its intermediate goal, residing in the local view. The shadow is a point in the direction to the intermediary goal inside a defined margin of 3 pixels. Our agent observes its local view and finds an abstract destination point, which is the shadow of the nearest intermediate destination, provided by the path planner. The first destination point is the destination point of the first episode in this plan, which resides in the local view. The agent starts moving from toward its abstract destination point, which is inside the local view. After achieving the intermediary goals, the environment updates the destination point of the next episode in its plan. The second module is our deep reinforcement learning, which is composed of a convolution of neural networks that receives the local view as the input and predicts the best action for that state. This part is responsible for avoiding obstacles and moving the agent safely in the near future. We select a region in the area of Halifax, Nova Scotia, with a bounding box with a specific longitude and latitude. We created a water and a land layer using public data on the Earth elevation using the NOAA3 dataset. We also randomly added some moving objects to play the role of obstacles in this simulated 2D environment. In this work, we dynamically generated the obstacles during an episode. We also defined a novel evaluation metric called RATD, which is the rate of arrival to the target. When we test our model, we randomly generate n sources and destination points. After that, we run the model and we measure the number of arrivals to the destination, which means the number of successful trips. And we consider it as the P. So using this formula, we calculate the RATD for each model. Now it's time to talk about the training and testing setup. Reward function is presented in this slide. If agent fails to reach to the target, it will be punished by a negative reward. If it reaches the target, it will get a positive reward. In a normal situation, the reward depends on the distance of agent from the target and obstacle. Delta D is the distance in geometry degree that an agent moved from the last episode. Psi is set to 1000. Delta OD is the distance of our agent from its nearest obstacle in geometry degree, and phi is set at 20. In this equation, we deducted Ka from the reward to encourage the agent to find the nearest path, and it was set at 0.01. The value of phi and Ka were manually tuned using a trial and error approach, and the values reported are those that provided the optimal performance for all methods. In our method, we use the target network to adjust the action values iteratively toward the target values. The application of a target network is to reduce correlations with the target. We use the replay buffer to eliminate the relation in observation chain and to soften fluctuation in the data distribution. And we use the same idea here. In our training phase, a training step includes 1000 episodes or plan randomly executed to update our neural network parameters. Each of these episodes or plans includes an undefined number of training steps. We store the agent state, the agent next state, reward, and the action in a replay buffer as experience. With the size of and the size of the replay buffer is 100,000. We retrieve 3,000 items from this replay buffer after every 100 training steps. Every 200 training steps, the parameters of our model are copied to our target network. These values were configured empirically by trial and error tests. In the training phase of our model, we use the idea of exploit and explore, which means the action of our agent is based on two types of learning. First, exploring the environment randomly and measure the gain reward. Second, exploiting the learned knowledge by using the parameters of a trained neural network. In this work, we assign the weight of 0.9 for the explore part and 0.1 weight for the exploit part. The weight of explore increases during the training phase. In order to evaluate the strength of our model in finding the best path to the destination, we increase the distance between the origin and destination points. In this picture, you can see the maximum distance between a source and a destination point in Halifax map is 0.32. To test our model, we increase this distance from 0.01 to 0.32. In this figure, you can see the effect of different distance on the rate of arrival to the target. From left to right, the RATD for the baseline and our proposed method with different distances. As you can see, the rate of arrival to the target drastically decreases when the distance between the source and destination increases in the vanilla vessel navigator, which is our baseline. However, the change in the RATD for our model is way too smoother than our baseline. Our model is presented in the figure B, but the baseline is in the figure A. In this picture, the change on the rate of arrival to the target is more obvious. In vanilla vessel navigator, the number of successful trips tends to zero when the distance increases between the source and the destination. However, our model is robust to these changes, and it doesn't affect on the number of successful trips when we use our model to find the best path from the source to destination. In this video, I want to present the performance of our algorithm in Halifax map. This red point is the source of the trip, and this green dot is the destination for that trip. This light green here is the first intermediary goal that the agent should attend to. These yellow points are the obstacles that exist in the water, but the agent ignores them when it tries to draw the plan to the destination. This picture here is the local view of the agent in each plan. So I played a video that you can see the performance of our model. Here the agent tried to reach to its intermediary goal, which is presented by this green square. So as you can see, the agent passes through all these obstacles and this land, and it can reach to this goal at each one of these local view. Actually, it can find the best path and the best route to reach to this target when the local view is really messy and it's full of the obstacles. But its performance is outstanding and it has the best approach to find the best path. And here you can see that how does it find the best route to the target by passing through all these intermediary goals. So to wrap it up, our proposed method takes advantage of two planning approach. One, long-term planning using a path planner with the assumption of no obstacle to generate a potential effective path. And two is the short-term decision making. This is output of our reinforcement learning model to avoid the dynamically generated obstacles and to navigate the agent in the near future. Our experiments show that the usage of a local view improves the performance of our basic model. However, its performance reduces when the distance between the origin point and the destination point increases. We address this weakness using a path planner to provide a potentially efficient path for the whole trip without the details of a movement. This is followed by a short-term decision maker to navigate agent safely. I should thank you for listening to our presentation and I hope that you find it useful for your own research. If you have any question, you can send the email to our group that our emails are included in our paper. Also, we have the Institute of Big Data that you can access to our code that is published on the GitHub and it's here. You can fork it to your own GitHub account and use it for your research. Thank you for your attention and best regard.